Hello YouTube. In this video we will go over vector spaces, subspaces, sums and direct sums. So without further ado, let's get started. Before giving the definition of a vector space, we will provide some motivation. So let's imagine a person in the plane. There they are. Our goal to help this person move in the plane using mathematics. So to accomplish our noble goal of aiding this person, we will proceed in the following manner. So what do we have in this picture? Well, we have our plane with a coordinate system in it where we will construct arrows. So here's V, an arrow. Next we have M. M will represent the process of us taking our newly constructed arrow, copy-pasting it at the feet of our person in their plane, and them moving along the arrow to reach their new location. And in their plane we also have a coordinate system, so we can refer to the points at which the person is located at. So now our person can move. Now we will attempt to formalize all of this. So first we will formalize the notion of an arrow. Well, to be able to draw an arrow, we need 2 points, and we need to know which of the points is the first and which the second, so that we know where to place the arrowhead. Well, for points in the plane, we can define points to be ordered pairs of real numbers. So a point P is just an ordered pair of 2 real numbers, x and y. Now we can define arrows to be ordered pairs of points. So the arrow A is just the ordered pair of points P1, P2. So here's an arrow, P1, P2. So this arrow has been uniquely determined. Now, since in our setup we're always drawing the arrow starting from the origin of the coordinate system, we can perform a conceptual simplification. We always know that the first point of the arrow will be the point 0, 0. So to determine an arrow, we only need to know the second point. Hence, when specifying an arrow, we will do so in the following manner. So our arrow A will just be equal to the point P, which is just an ordered pair of real numbers. So this is our setup, so we can do this because we've determined to always draw our arrows starting from the origin of our coordinate system. So those are arrows. Now we would like to formalize our process M, and we will formalize that as a function that takes in as inputs arrows, and then as an output gives us the new position of our person, the one they arrive after they've moved along the given arrow. So what's happening? We make an arrow V using M, we send it to our person in their plane, it appears at their feet, and then they move along it to reach their new position. So now we would like to define a function capital M that does this, that achieves this notion of, captures this notion of moving. So we would like our M of our vector V to be equal to the coordinates of the point to which our person moves after following the arrow we've handed them. So let's try and figure out the coordinates of this point over here. Well, we know the coordinates, the original coordinates of the position of our person before they've moved. So some point P, and the coordinates are xp and yp. And after moving along V, they reach this point, and this point has these coordinates. Well, to reach the new x coordinate, our person has to move xv to get to xp, as we can see. So this length plus this length, and this length is just equal to the projection of our arrow onto the x-axis, and this is the y projection. So this length plus this length gives us the new x coordinate. Same goes for y. So we see that M of v is equal to xp plus xv and yp plus yv. So we just add coordinates. So we define our function m to be the following. So we give our arrow v in. Our v is an ordered pair of real numbers. We know the previous position of our person, and we just add these numbers together to get this, the new position. So that would be capital M. Now we would like to define addition for arrows. So to figure that out, we will specify two different arrows, v and w. We'll use our function app to map those two arrows and make our person move. And from the observations we establish by observing our person moving, we will work backwards to fashion a satisfying definition for arrows. So when we add these two arrows, I would like to get another arrow. What kind of arrow? That's what we're going to figure out using M. So when I give my person the arrow V using M, well, they'll move like this. And then if I give them W after having given them V, they will move from this location to this. So they will do this movement. Well, we can draw an arrow from this point to this point. So if they go this way or they go directly this way, the result is the same. So I would like for the definition for my addition of two arrows to be equal to this arrow over here, which corresponds to this movement over here. So I would like the sum of my two arrows to be such that when I apply M to them, I get the same as this arrow over here. Well, let's try and see what the coordinates of this point over here are, P2. So at the start we just have P, and then at the first step we give our person V using M, and they move to P1, which is just this point over here, which we get by using the definition of M. And now we treat P1 as the starting point, and we use MW, so we get this new point over here, which is equal to P2. So now I want the sum of these two, when I apply M to the sum of those two arrows, which would give me some arrow, again, which is just an ordered pair. So it would have xp in it, yp in it, and some x offset and some y offset. And this has to be equal to this over here. And ordered pairs are equal if and only if, well, their first entries are equal and their second entries are equal. So for this expression to be equal to this, we see that this big X has to be equal to this sum, and this Y over here has to be equal to this sum. So this provides us with the following definition of addition, where we just go V plus W should be equal to this over here. So that's addition. This will give us the desired arrow, which is equal to this arrow. This arrow just placed at the starting point of this arrow would be at the origin of the coordinate system. So, and here are some properties of addition. Addition is commutative, associative. There exists our neutral element, which is just the zero arrow, just the ordered pair of 0, 0. And we have that for each arrow V, there exists a corresponding inverse element. So if you go V plus that inverse element, you just get 0. So in this case, since we're dealing with ordered pairs, if you just take an arrow V, which is equal to this ordered pair over here, and if you just add this ordered pair with minus xv and minus yv, then you would just get 0, 0. So you would get the 0 arrow. So that's addition. The inverse element for a given arrow motivates us to consider introducing the following operation called scalar multiplication. So we have alpha, which in our case is a real number, and we have v, which is an arrow. So alpha times v will be equal to this over here. So we just multiply the coordinates of v using alpha. Geometrically, this would correspond to the following picture. So we have V, our arrow, and if I take some alpha, which is positive, and whose value is greater than 1, then multiplying alpha times V, we get a new arrow, which is just a stretched version of V. So it has the same direction, it's just stretched. While if I were to take a positive alpha, whose value is between 0 and 1, it would shrink this arrow to something inside of V, so the length would be less than V. And if we take alpha to be negative, so in this case I took alpha positive, so minus alpha is negative, so this times V would just equal to some stretched or shrunk version of V, but the direction is flipped. So that's how scalar multiplication can be geometrically understood when dealing with arrows in the plane. So some consequences of the definition, we have that if you multiply V by -1, well, you can just get the inverse element of V. If you multiply any vector, any arrow by 1, you would just get V. If you multiply the 0 arrow by alpha, you would get the 0 arrow. So, and now that we have scalar multiplication and addition between arrows, we have that this relationship holds, so distributivity, so alpha times the sum is the same as if you were to first multiply the separate arrows and then add them together. So that's for multiplication. So we've gotten all of this out of our toy problem of the plane. Now we want to generalize. All of this was done using the geometric intuitions we have for the plane. Similarly, we could have done this for 3D space. But what if we want to be able to deal with higher dimensional spaces? We have no geometrical intuitions to aid us in even understanding what something like that would mean. But we do have all these non-geometric properties that our toy model of arrows in the plane, equipped with addition and scalar multiplication, satisfies. Hence, we define a vector space is a set V along with an addition on V and a scalar multiplication on V such that the following properties hold. So we demand commutativity for addition, we demand associativity, we demand that there exists some additive identity, we require that there exist additive inverses for every V, which we will call vectors, so elements of V are vectors. So for each vector there exists its additive inverse, which is also a vector. We require there to be a multiplicative identity in F, and F will be the set of scalars. So when we want to do scalar multiplications, we multiply with elements from F. And F will, in our case, be either the set of real numbers or the set of complex numbers. So there exists a 1 in the set of scalars, which acts like this as an identity, and we require for the distributive property to hold. So these are all the properties we saw our toy model exhibit when we defined it the way we did and provided addition and multiplication. So now we treat any set V that has some operation, addition, and some form of multiplication. If it exhibits these properties, then we consider it a vector space. So some examples. So we define f of f to the nth power to be equal to the set of all of these n tuples, so like ordered pairs, just n coordinates. So if we have this set, and if we define addition to be equal to this, and scalar multiplication to be equal to this, well then it turns out that this is a vector space again. So f in our case will be either the set of real numbers or the set of complex numbers. Now for another example, so polynomials, So a function p, which maps from our scalars to the scalars, is called a polynomial with coefficients in f if there exists a0 to an, which are scalars, such that p of z is equal to this. So this is a polynomial, and now we let p of f be the set of all polynomials in f, and we define addition between polynomials to be equal to this and scalar multiplication to be equal to this. And as it turns out, now the set of all polynomials with addition and scalar multiplication defined like this is a vector space. So again, we started off quite geometrically with our toy problem in the plane. So arrows, very geometric thingies, objects. And now it turns out that even polynomials in some abstract way can be treated as arrows or points in space, just in higher dimensional space, which we don't have any geometrical intuitions for, but all the algebra still holds. So the set of all polynomials is a vector space. Now that we've gotten the definition of a vector space out of the way, we can prove some properties that vector spaces have. So for example, a vector space has a unique additive identity. In the definition, we only stated that a vector space needs to have an additive identity, but we didn't demand for it to be unique. But it turns out it has to be unique. So suppose that V, our vector space, has two additive identities, 0 and 0 prim. So since they're additive identities, these relations hold. Well then, 0 prim is equal to the following, and then we use commutativity, and we just get that 0 prim is equal to 0. So we pick two arbitrary additive identities, and it turns out that they're the same. So there is only one additive identity in a vector space. Moving on, we have that every element in a vector space has a unique additive inverse. Again, we just stated that each element has to have an additive identity. We didn't demand for it to be unique in the definition. So suppose again, just like with the additive identities up there, suppose we have two additive inverses for some arbitrary vector v in our vector space, then this holds, and then we have that w prim is equal to the following, and we can write 0 this way. We use associativity to bracket the terms how we like, and then this is 0. So we get that w prim is equal to w. So again, additive inverses unique. Now we have that if you take some vector v and you multiply it by the 0 from the field of the scalars, well then you just get the 0 vector. So how to show this? Well, 0 times v can be written like this. Then we use distributivity, and now we use additive inverses to both sides of this equation. We add the unique additive inverse minus 0v, and then we get that, well, 0 times v is equal to the 0 vector, because this cancels. Now we have that if you take any scalar from the field f and you use that to multiply the 0 vector, well then you just get the 0 vector. So a times 0 is equal a times, we write just 0 this way. Distributivity, again, add additive inverses, and we get what we wanted. And at the end, we have that if you take some vector v from our vector space and you multiply it by the scalar -1, then you get the additive inverse of v. So v plus -1 times v, we can use distributivity to pull out the v, then we get this. Well, 1 plus -1 is just equal to 0. So we get 0 times v, and we've shown that is equal to 0. So this, when you add it to v, gives you 0, so this has to be the additive inverse of v, and there is only 1. So -1 times v has to be the additive inverse of v. So that would be for the properties of vector spaces for now. Now we introduce the concept of subspaces. So what is a subspace? Well, if we have some subset U of our vector space V, then we will call that subset a subspace of V if and only if U is also a vector space using the same addition and scalar multiplication from our vector space V. So it's a smaller set inside of V that is also a vector space when you take addition and scalar multiplication from the bigger vector space. So now we have the following result that will enable us to quickly check whether some given given subset is a subspace. So the subset U of our vector space V will be a subspace if and only if this condition holds. So you take two arbitrary vectors from U, you take two arbitrary elements from U, you take any arbitrary alpha scalar from F, you form this element, and you ask yourself, does it belong to U? If it does, then U is a subspace. So let's prove this. So to show equivalence, we have to prove two implications. So first of all, let's suppose that U subset of V is a subspace. Well, we take two vectors from U, we take a scalar alpha from F. Since U is a subspace, it is a vector space, that means that alpha times Y does belong to U. And then when we add X and alpha plus Y, since it's a vector space, the addition is closed. So this element belongs to U. So we've proven one implication. Now the other implication, let's suppose that our condition holds. So whatever two elements I take from U and whatever scalar F I take from F, and when I form this, it does belong to U. So now we have to show that U is a subspace. Well, the properties of commutativity and associativity and such are already solved or are already possessed by U due to it being a subset of V and inheriting addition and scalar multiplication for V. So the things we have to check that only remain for us to check to establish that U is indeed a vector space is, for example, we have to check whether does the zero belong to U, because we could take a subset of V without including zero. So does zero belong to U? Well, let's set y equals to x and alpha equals to -1. Then we have that x plus the additive inverse of x belongs to U. So x plus this is equal to 0, so 0 does indeed belong to U. Well, now we ask, is addition closed? So just set alpha to equal to 1, and then we get that x plus y belongs to U. And is scalar multiplication closed? Well, set y equals to some vector U, just notation-wise to make it look prettier. So set x to be equal to the 0 vector, and then we get that 0 plus alpha times U is equal to alpha times U, and that belongs to our subset U. So whatever vector U I take, and if I multiply it with any alpha, it does belong to U. So scalar multiplication is closed. We do not go outside of the subset U. So that means that U is indeed a vector space, so U is a subspace. So here are some examples of subspaces in R2, R squared, so the plane. So these lines passing through the origin are subspaces. So if you just look at this axis, or if you look at this line, those are all subspaces, and any other line that passes through the origin, no matter the angle it forms with the x-axis. So those are subspaces. Whilst this line over here is not a subspace, since for example, it does not have 0 in it. It does not pass through the origin, so it cannot be a subspace. So now we're introducing the concept of a sum. So what is a sum? Well, suppose we have subspaces of V, U1 to UN, and their sum, denoted this way, will be equal to this set over here. So I take vectors from each corresponding subspace, I add them up together, and that vector goes into the set, into the sum. So now we have the following result. We have that the sum of subspaces is also a subspace of V. So let's suppose these are subspaces of V. And now to show that this sum over here is a subspace, we're going to use this previous result we've established for testing whether a given subset of a vector space is a subspace. So we will take two elements, V and W, from the sum. We will form this sum over here. So we pick some alpha, an arbitrary scalar from the field F. We form the sum, and now we ask ourselves, does this belong to the sum? So since V belongs to the sum, that means it can be expressed in this way as the sum of corresponding vectors, which I will denote this way. And same goes for W. It can be expressed as this sum over here. So now we write that out. We write what this sum over here actually is. So it is all of this. I have already multiplied W with alpha. So we get this. And now we group terms. So U1 prim plus alpha U1 secundum. So this term plus this term, and I group them, and I do all of that for each of the corresponding terms. So here's that, and here's the n. So now, since U1 to UN are subspaces, this sum over here belongs to U1. And so on for all of these brackets. So all of these sums represent some vectors that belong to their corresponding subspace. So U1 to UN. Well, that means that we can write this sum as some combination of some vectors U1 to UN, where these vectors belong to their corresponding subspace. But that means that this is of this form, and that satisfies the definition of being an element of this sum. So we have that V plus alpha times W belongs to the sum. Hence, the sum is a subspace of V. Now, we show the following. The sum of subspaces contains each given subspace. So U1 is a subspace of the sum, UN is a subspace, and so on. How to show this? Well, just take some vector uj from the corresponding subspace, big uj, and I can write uj in the following way. So zeros plus uj plus zeros. And now since all of my u's are subspaces, they all contain the zero vector. So I've written uj as this sum over here, so that means it satisfies the definition of belonging to the sum of subspaces. So whatever element I take from my corresponding subspace uj, it turns out that it also belongs to the sum. That means that uj, my subspace, is a subset of the sum. So this shows that all of these subspaces are contained within the sum. Now, if we imagine a subspace S that contains each given subspace U, then that imagined subspace would also have to contain the sum of those subspaces. Due to being a subspace, it has to contain all the sums of vectors of the subspaces inside of it. So let's imagine we have some S, which is a subspace of V, and S is such that all of these subspaces are contained within it. So, since S contains all of these subspaces, and it's also a subspace in its own right, well, if I take vectors from the corresponding subspaces and I add them up, all of those vectors belong to S. S is also a vector space since it is a subspace. So that means that this sum belongs to S. So that means whatever element I take from my sum of subspaces, that element also is contained within S. That means that this sum is a subspace of S. So what does this establish? Well, this establishes that the sum of subspaces is the smallest possible subspace that contains each of the subspaces U. So we have this, which is analogous to, for example, if we had numbers and m is some sort of smallest number satisfying a property, well then we would have that m is less than or equal to than any other number s that satisfies that property. So since it is the smallest, it is guaranteed to be less than or equal to than any other number s that satisfies whatever given property we demand of it. So this is analogous to that, where less than or equal to here is being represented by being a subspace of a set. So this is the smallest subspace that contains each of these given subspaces separately. So here are some examples of subspaces. If we're in looking at all the order triplets of real numbers or complex numbers. So U is just all of these triplets where we just plug in the first coordinate, we just plug in X. If we pick up all of those, well, that's a subspace. Same goes for this. And if we add up these two subspaces, their sum would be equal to these triplets over here. So here's a visual example. If I look at this set, so we're in the plane, and if I take all of these ordered pairs where the y coordinate is 0, and we can just control the x coordinate. If I pick up all of those vectors, we would get all the vectors lying on this x-axis, the horizontal line. And if I take this set containing all the ordered pairs where 0 is the first coordinate and y the second coordinate, well, then I would get this axis over here. And now if I sum up these two subspaces of the plane, well, I get the whole plane. I get all ordered pairs. Now we introduce the concept of direct sums. So what will a direct sum be? Well, suppose we have subspaces of V labeled this way, and we say that V is equal to the direct sum of these subspaces if and only if every vector V in our vector space can be written as the sum of corresponding vectors from our subspaces, and this representation is unique. So sums versus direct sums. Sums, if a vector space is a sum of subspaces, then that means that every vector is representable as a sum of this form. But the representation does not have to be unique. There could be multiple ways of expressing the same vector V as sums of all sorts of vectors from our corresponding subspaces. But if something is a direct sum, then there is only one way to express V using the vectors from our subspaces. So that's the key difference. Unique representation. So some examples, if we have this subspace and this subspace, well, they form a direct sum of all the ordered triplets of F. And if we define our UJs to be this, where all the other coordinates besides the jth coordinate are 0, and then we add up all those subspaces, again, we get the ordered n-tuples of F, and the representation is unique, so it's a direct sum. So how to check whether some subspaces form a direct sum of V? Well, we have to check that V can be represented as just a regular old sum of the subspaces. And the second condition that ensures the uniqueness of the representation is that if we try to express 0 as some combination of vectors in the sum, then it follows that all of these vectors have to be 0. So the only way to express 0 as a sum of vectors from our corresponding subspaces is to have all of these vectors be equal to 0. So 0 needs to have only this representation. And if these two conditions hold, well, then V can be written as a direct sum of the subspaces. So let's prove this. First implication, we suppose that our vector space V can be written as it is a direct sum of our subspaces. Well, if our vector space is a direct sum of these subspaces, then it is also just a regular old sum of these subspaces. So A holds, let's check B. So 0 can be written this way, and since our vector space V is a direct sum, then that means that this is the only representation of 0. This can be the only one. So we know that this is one way to represent 0 as a sum of corresponding vectors from our subspaces, and since V is a direct sum of those subspaces, well, then this is the only one by definition. There is no other way to express 0. So U1 to UN all have to be 0. So B holds. Now let's go the other way. So let's suppose that our two conditions hold. So V is a sum of these subspaces, and if we try to express 0 as the corresponding via the corresponding vectors from our subspaces, then it follows that they have to be 0. So let's suppose that some vector V in our vector space big V has two representations. So there's two ways to write out V using the corresponding vectors from subspaces. So we suppose this. And now since V is equal to V, we can equate these two. So we have that this representation is equal to this representation. And now we just transfer all of these terms to the left, we group them, and then we have the following. So U1 prim minus U1 secundum. Well, this, since all of these U1 prim belongs to U1 and U1 secundum belongs to U1, and this is just addition, so this whole difference belongs to U1, and the same goes for all the other brackets, all the other groupings of elements. So we have that this can be written as the following sum, so just some vector U1 plus all the way to UN is equal to 0, and now we use B. We use that, we've supposed that B holds, so we have this sum over here is equal to 0, and the only way to express 0 by our supposition is for all of these vectors to be equal to 0. But then that means that all of these corresponding differences, so U1 prime minus U1 secundum, where I goes from 1 to n, is equal to 0, well, that means that Ui prim has to be equal to Ui secundum. So all of these are equal. So that means that the two representations are actually the same. So whatever two representations we take for V, it turns out that they match. So there is only one representation. So we've shown that V is indeed a direct sum of our subspaces. And one final example. So we have these subspaces, and they do form a sum of this given vector space, so of f to the third. We can express all ordered triplets of f using the vectors in these subspaces. So if I take some arbitrary order triple from f to the third, we can express it, for example, this way, which all of these are elements belonging to these subspaces. So this is from U1, this is from U2, and this is from U3. So f to the third can be written as a sum, but the zero vector in f to the third can be written, for example, in this way, and it can also be written this way. So it turns out the zero vector does not have a unique representation, so that means that f to the third cannot be a direct sum of these subspaces over here, due to 0 having two different representations. So that would be it for today. In the next video, we will go over exercises in the textbook to review the material. And yeah, look forward to that. Thanks for watching. Have a good one.